We have an interesting question today about arithmetic progressions. They're sometimes called arithmetic sequences. So here we go, ENC. They're, I think modern day, they're more frequently referred to as arithmetic sequences. Now, a finite arithmetic progression or sequence is a series or sequence of terms that is separated by a common difference. Here that common difference would be 30, right? And so 7 plus 30 is 37, 37 plus 30 is 67, and so on. Now, what's notable right here is all of these numbers are prime. 7 is a prime number, 37 is a prime number, all the way out to 157, which is prime. And then all of a sudden we run into the seventh term in the sequence that's not prime. It can be written as 11 times 17. That's 11 times 17 is 187. And note that this is the seventh term. Okay. So our overarching question here is, can you have an infinite arithmetic progression or sequence with only prime terms? Now here we started out with 6, right? 1, 2, 3, 4, 5, 6 primes, but then we ran into a prime term, which was the seventh term. But again, we want to show conclusively that this can't happen, meaning that you can't have an infinite arithmetic progression with nothing but prime terms. Now this went all the way out to 6, but then the seventh one was not prime. Okay. Now let's take a look at the more general form here of what an expression or an arithmetic sequence would look like. Each of the terms in this sequence would be of this form an plus b. Let's let p just be an arbitrary prime such that this is true, okay? Such that a and p, in other words, this is another way of saying that a can't be a multiple of p. But notice if we can find a solution to this equation, that would be the answer to the question is no, because this a plus b would be divisible by p. Meaning you could write a plus b. Let me write it directly above here. If we can find such an n, that would mean that an plus b is equal to some multiple of p. All right, that's just an equivalent rendering of this congruence right here. Okay, if we can find an n, which it's very easy to find such an n, but anyway, so this would be a term in the sequence that was not prime, right? And so that once we prove this, we've answered the question is you can't have an infinite arithmetic progression with only prime terms. Now, it turns out crucial to a solution existing is the fact that a and p are relatively prime. Now, what that does, I think it's called Bezier-Outz, or it comes from the division algorithm. But notice right here, another way of rewriting this is you can rewrite this as ax is equal to 1 minus a multiple of p. But yet another way of writing this, which is more useful right here, is you can say ax is congruent to 1 mod p. That's an equivalent statement. Okay. Modulo p. But what does that mean, folks? That means that x is the inverse. In other words, you can write down here x would be equal to the a inverse we're looking for. That's what we mean by an arithmetic inverse. Okay, it's very analogous to what goes on with just regular numbers. For example, normally just with regular numbers, real numbers, a times a to the minus 1, right? And this is in the real number realm, or I guess complex number 2. That's equal to a times 1 over a, right? Now, the form here is not the same form, but it's the same idea. A times 1 over a is certainly equal to 1, right? Okay, it's the very same thing right here, except we're doing it at the congruence level, right? So this this x that we get, which comes from the division algorithm, you don't always have to do the division algorithm. You can kind of just guess what the inverses are by inspection. But we get what we need here, okay, because we now know that there is a solution. This would be the solution. There is an n Okay, there is an n that satisfies this condition, but this condition would indicate that you had a non-prime term in the sequence. Okay, so we're done with the proof. So the answer is, of course, after that demonstration, hopefully the answer is no. Now let's do a concrete example. Okay, this is just the one we just worked, folks. This is the one we just worked, 30n minus 23, or the one that was the example up here, 30n minus 23, okay? Now so this, seeing is believing, right? So what we can do is just use the result we just established. Now notice here, we reduce mod 11, 23 is equal to 2 times 11 plus 1, that's where this 1 comes from, okay? Then 30 is equal to, what do we got here? 30, you can replace 30 with 8, right? Because 30 is equal to 2 times 11 plus 8. All right, so we reduce this thing mod 11, then it's not hard to show that 8 inverse is the same as 7. And I'll do that. So we get n is congruent to 7. I'll show you why in just a sec. Mod 11. Now, if you recall, we did get the 7th term. So you see, that's kind of cool. If you remember, this 7 that you see right here is the same as the 7th term that we observed right here, right? So see, we just did this manually and say, oh, a 7th term is not prime. But now we've shown rigorously that the 7th term lines up with this 7th term up here, okay? Now, so where did we get the 7? Okay, where did we get the 7? Well, the 7 happens because 7 times 8 equals to 56. And again, a lot of times you could do this with a division algorithm. It's just better to do it by inspection, usually for small moduli. But 7 times 8 is equal to 56. And 56 is certainly congruent to 1 mod 11 because 56 minus 1 is 55 and 5 times 11 is 55. Okay? So 7 times 8 is equal to 56, but that's congruent to 1. And of course, we're talking mod 11 here. So I kind of like that because you actually see it happening. And that means that for any prime, you can always produce a term in an arithmetic sequence that is not a multiple of that prime, which means you never can have that happen, okay? You never can have what we thought happened. There's no such thing. There's some that go out a long ways, but in any event, let's see, what do we have here? So that right here, that would make this the same thing as 8 inverse, right? If you want to just stick to the notation. All right, folks. But again, the overall answer to the question is no. We proved that generally right down here. Thanks for viewing.